Hello, chemists. My name is Kim, and today we have one learning goal and one learning goal only. We are going to be looking at full written chemical redox reaction equations, and we are going to be practicing breaking them into their component parts. The half reaction that describes oxidation and the half reaction that describes reduction. We're also going to work to make sure those half reactions are fully balanced so that we are conserving electrons on both sides of the equation. A quick reminder from a previous lesson, oxidation refers to the loss of electrons, while reduction is the gain of electrons during a chemical reaction. Oxidation and reduction must always occur together because for electrons to be lost and gained, they have to come from somewhere and they have to go somewhere. Reactions in which oxidation and reduction reactions occur at the same time are known as redox reactions. When one part of the reaction gets oxidized, the other part gets reduced. We are going to be writing half reactions to try and parse out which part of the redox reaction is being oxidized and which part is being reduced. The abbreviation that chemists use a lot to remember this is oil rig. Oxidation is losing, reduction is gaining. To start, let's take zinc and react it with copper sulfate to form copper plus zinc sulfate in a single replacement reaction. Single replacement reactions are probably going to end up being redox reactions. The first step to writing this half reaction is going to be determining the starting oxidation states of the ions that are involved. So because SO4 stays together throughout the reaction, I'm going to focus on zinc and copper to start. And let's see if we can do this without needing to figure out the oxidation state of sulfur and oxygen. So I'm just going to make room for myself to write down the starting and the final oxidation states of zinc and copper, and then I'm going to grab my periodic table, and I'm going to find zinc and copper, which are conveniently right next to each other on that table. Now, don't get tricked. Remember, when zinc is by itself, nothing bonded to it, its oxidation state is always 0. Then looking over at the product side, zinc only has one possible oxidation state according to the periodic table, so it will be +2. Copper, on the other hand, has two possible oxidation states. Copper could be either +1 or +2. Now this is where going and finding sulfate on table I will be helpful for me. So sulfate, according to table I, that polyatomic ion there, that has a charge of -2. So that tells me that in order for there to be a neutral compound between one Cu and one sulfate ion, copper must have an oxidation state of +2 at the beginning. At the end, copper is by itself, so it will have an oxidation state of 0 as an element unbonded to anything else. So the first thing to do when trying to figure out how to write a half reaction is to determine the starting oxidation states and the final oxidation states of the ions that are relevant. Sulfate we would call a spectator ion in this reaction. It is not changing its oxidation state before and after the reaction occurs. So I can see here this is a redox reaction because zinc and copper both change their oxidation states. My next task is to identify which element is being oxidized and which was being reduced. For this, I want to remember the key phrase that I use, oil rig. Oxidation is losing, reduction is gaining. So zinc, to go from an oxidation state of 0 to +2, would need to lose 2 electrons. Zinc is being oxidized. I'll start by writing my half reaction for oxidation. I'll worry about reduction in a moment. Let me just think about zinc. So I'm starting with a neutral zinc atom with an oxidation state of 0, and I am forming a zinc ion with a charge of 2+. That means I am losing zinc 2 electrons. So I'm going to write +2 electrons on the product side of the reaction. That's where the electrons go in a reduction or in an oxidation half reaction anyway. For reduction, I'm going to notice that copper is going from having an oxidation state of +2 to an oxidation state of 0. It is reducing its charge because it is gaining electrons. So the copper 2 ion is gaining 2 electrons to become neutral copper. And here are my half reactions. I've just written them. That's really all that it is. I just take the 2 parts of my reaction that are being oxidized and reduced and split them apart. Notice I have not included SO4, sulfate, in either half reaction. It's not changing its oxidation state, so it's not involved in the redox part of the reaction that I will write. The last step that I might take, and in this particular case, it's not necessary, but notice zinc is losing 2 electrons, copper is gaining 2 electrons. That works, 2 electrons, 2 electrons. I might, however, have a situation where I don't have the same number of electrons being lost as gained. And if that were to happen, I would need to balance the equation. This is already balanced, so I don't need to do it. So here are my half reactions for zinc and copper. The oxidation reaction shows neutral zinc becoming a zinc ion plus 2 electrons. The reduction half reaction shows a copper 2 plus ion gaining 2 electrons to become neutral copper. Let's look at a second example. This time, let's take aluminum and react it with copper chloride, CuCl2, and we will form solid copper plus dissolved aluminum chloride. We're going to again start off by determining the starting oxidation states of aluminum and of copper. I'll grab my periodic table and look at the top right corner and see that aluminum has one possible oxidation state, +3, right? No, be careful here. This is a mistake people make all the time, right? Don't get tricked. Aluminum is by itself at the beginning of this reaction. It is not bonded to any other element, so it actually is starting with an oxidation state of 0. Don't forget that. Copper, on the other hand, has 2 possible oxidation states. So I want to look at chlorine to see which oxidation state, +1 or +2, is more likely for copper. So chlorine only has one possible negative oxidation state, and that's -1. And there are 2 chlorines bonded to the copper, which is -2 total. So to make a neutral compound, that copper must have an oxidation state of +2. Now, on the other side of the equation, the final oxidation states, copper is now by itself, and aluminum is now bonded with chloride. I'm going to do the same math that I did for chlorine's oxidation state to figure out aluminum's oxidation state, and it's +3. It does turn out that is the only possible oxidation state for aluminum, so that works out. And the oxidation state for copper is now going to be 0, because now copper is not bonded to any other element. It's by itself. Now, aluminum is going from having a charge of 0 to a charge of +3. To get a positive charge, that means aluminum must be being oxidized, or aluminum must be losing electrons. Oxidation is losing. So to write aluminum's half reaction, I'm going to write aluminum, Al, neutral, is reacting to form an aluminum 3+ ion plus 3 now free electrons. Over in the reduction half reaction, copper is going from having an oxidation state of +2 to having an oxidation state of 0. Its oxidation state is being reduced because it is gaining 2 electrons. So I'm going to put my electrons on the reactant side to form neutral copper. So notice 3 and 2 are not the same number, right? Aluminum's losing 3 electrons, copper's only gaining 2. That can't work. We have to have conservation of mass. So we're going to balance our electrons here. And I'm going to move the oxidation state tags out of the way. And we are going to use some of our balancing equation skills. This is actually going to end up giving us the same result that we would get if we just balanced a reaction the way that we may have already learned how to. We can also balance the half reactions and actually end up with the same balanced equation. So let's take a look. Now I've got 3 electrons from aluminum, 2 electrons from copper. I need to find the least common multiple for both 2 and 3 so that they can equal each other. So for whole numbers, the least common multiple that I can get for them is going to be 6. So let's say that I need aluminum to be losing 6 electrons and I need copper to be gaining 6 electrons. Now I need to look at what I just did. So I multiplied 3 times 2 to get aluminum to equal 6 electrons. So I'm going to put 2 in front of all the other aluminums. And I multiplied 2 times 3 to get copper to have 6 electrons that it was gaining. And so to balance this equation, I'm going to go put those coefficients in the same places in the balanced chemical equation, just to make sure that I am balancing my half reactions to balance my equation. Let's try a practice problem. As always, there's a lot of information in this word problem. It may not all be super necessary. Early scientists defined oxidation as a chemical reaction in which oxygen combined with another element to produce an oxide of the element. An example of oxidation based on this definition is the combustion of methane. The definition of oxidation has since been expanded to include many reactions that do not involve oxygen. An example of oxidation based on this expanded definition is the reaction between magnesium ribbon and powdered sulfur when heated in a crucible. The reaction is represented below. Write a balanced half equation for the oxidation that occurs in the reaction represented by equation 2. Pause the video if you need more time to write down the reaction. Remember, our first step is going to be to write the oxidation states of the elements before and after the reaction. So I'm going to find sulfur and magnesium on my periodic table, but remember the rule about elements by themselves. Both magnesium and sulfur are starting off with oxidation states of 0. And then after the reaction, magnesium only has one possible oxidation state, positive 2, which means sulfur's oxidation state must be negative 2. Since oxidation is losing electrons, my half reaction is only going to show what is happening to magnesium as it is losing 2 electrons to become Mg2+. Let's try another. Copper can be used for water pipes in homes. When the pipes corrode, copper atoms oxidize to form Cu2+ ions in the water. A homeowner has a water quality report prepared for a sample of water taken from pipes in the home. According to the report, the 550-gram sample contains 6.75 times 10 to the negative 4th grams of dissolved copper 2+ ions. Write a balanced half reaction equation for the corrosion that forms copper 2+ ions. This is really a word problem. So the problem says that for corrosion to occur, neutral atoms form copper 2+ ions. The question doesn't ask us this, but this would be oxidation. So copper forming copper 2+ ions would be neutral copper, arrow, copper 2+ plus the 2 electrons, because the copper 2+ plus the 2 electrons would equal neutral copper. One final question. A small digital clock can be powered by a battery made from 2 potatoes and some household materials. The potato clock battery consists of 2 cells connected in a way to produce enough electricity to allow the clock to operate. In each cell, zinc atoms react to form zinc ions. Hydrogen ions from phosphoric acid in the potatoes react to form hydrogen gas. The labeled diagram and balanced ionic equation below show the reaction, the materials, and the connections necessary to make a potato clock battery. You are going to write a balanced half reaction equation for the oxidation that occurs in the potato clock battery. Pause the video if you need more time to think about it, and notice that the reaction is giving you the charge of the ions involved in some situations. So we're going to start by annotating our reaction with the starting and final oxidation states. Zinc starts off by itself with an oxidation state of 0. Hydrogen is explicitly labeled as having a positive 1 charge. So the reason that that hydrogen has a positive 1 charge is because it says H+. Similarly, at the end, zinc ion 2+ is told, we are being told that its oxidation state is 2+. And hydrogen on its own at the end of the reaction has an oxidation state of 0. So the oxidation half reaction would be zinc losing 2 electrons to form zinc 2+. Let's check back in. Hopefully you feel more confident using a redox reaction as it's written to determine the oxidation states of both of the elements that are being oxidized and reduced before and after the reaction, and then determine the half reactions that are involved. Nice job today.